Today we will discuss about specific conductance, equivalent conductance and molar conductance. After that, we will solve some numericals related to it. Most often, very often, students get confused about converting specific conductance into equivalent or molar conductance. So today we will discuss about this. So आज हमें जो है स्पेसिफिक कंडक्टेंस, इक्विवेलेंट कंडक्टेंस एंड मोलर कंडक्टेंस का रिलेशनशिप को डिस्कशन करना है और इसके बाद न्यूमेरिकल्स को सॉल्व करना है, ठीक है। सो देखो क्या है कि अगर हमको इक्विवेलेंट और मोलर कंडक्टेंस को समझना है तो स्टेप वाइज हमको स्पेसिफिक कंडक्टेंस, फिर इक्विवेलेंट कंडक्टेंस, फिर मोलर कंडक्टेंस इसको डिस्कशन करना है। कैसे? So let us first discuss the specific conductance, and before going into specific conductance, consider a conductor of length L and area of cross section is equal to A. And from physics you know resistance of a conductor is directly proportional to length. That is, higher long is the conductor, higher will be the resistance. And again, R inversely proportional to the area of cross section. Thickness of the conductor allows the electron easily pass through it, so resistance decreases. So from these two equations you can write by combining them R directly proportional to L by A. Resistance directly proportional to L by A. When we equate them with the equal symbol, we need a proportionality constant. Here we write the rho, that means we call it the proportionality constant or specific resistance, rho L by A, where rho is the specific resistance, or sometimes we call it resistivity. Okay. So this is the first equation using which we will proceed. So R is equal to rho L by A. So once you get R is equal to rho L by A, and as you know the conductance is the inverse of resistance, so C is equal to 1 by R, that is 1 by this. So 1 by 1 by rho, and this will give you A by L. Inverse of resistance is the conductance, and inverse of the resistivity is the conductivity, or inverse of the specific resistance is the specific conductance. So we get C is equal to kappa means 1 by rho A by L. Okay, so the conductance is equal to specific conductance, where kappa is equal to specific conductance, or is equal to conductivity, Are you getting it? So you see now specific conductance or conductivity. So we'll now define this specific conductance. Okay. See, if we'll take the area of cross section to be 1 centimeter square and length to be what? 1 centimeter, then 1 by 1 becomes 1, so kappa becomes conductance, specific conductance becomes equal to conductance. So we can define in this manner the specific conductance of a conductor, specific conductance of a conductor is equal to the conductance when length of conductor is 1 centimeter and area of cross section is 1 centimeter square. Are you getting now? 1 centimeter square. Like this we can define specific conductance. Problem is, this is about the conductor. We are not interested with the conductor. We are interested with the solution. How to determine the specific conductance value of the electrolytic solution. So, what happens? How to calculate? So, we'll have to take this area of cross section and length. You see, if area of cross section is equal to 1 centimeter square and length is 1 centimeter, then the volume will be area into length is equal to 1 into 1 centimeter cube. Centimeter square to centimeter gives you 1 centimeter cube. 1 centimeter cube is nothing but 1 cc. 1 cc is nothing but 1 ml. So very simply, the conductance of 1 ml solution is called the specific conductance. For solution, conductance of conductance. But how is it measured? It is measured in a conductivity cell. You have the formula C is equal to kappa A by L, right? Kappa A by L. Okay, so implies kappa, you take L by A here, kappa is equal to C L by A. In the conductivity cell, when we want to measure the specific conductance, the electrodes are placed like this, in between which the distance of separation is 1 centimeter. Distance between two electrodes. The separation between two electrodes inside the conductivity cell is 1 centimeter, and area of the cross section of each electrode is 1 centimeter square. Length is 1 centimeter, distance between the separation between two electrodes, and area of cross section is 1 centimeter square. So in every conductivity cell, since this is fixed, that means L by A is always fixed, its value is constant, is called the cell constant. This is called the cell constant. Whatever, okay, solution is used, the cell constant is always constant. Taking the advantage of which, we will later see how specific conductance is converted to equivalent conductance. So you are now clear. So the conductance of 1 ml solution is the specific conductance measured in a conductivity cell in which the distance of separation is 1 centimeter and area of its electrode is 1 centimeter square. So now let us see the disadvantages of measuring specific conductance. Let's consider two different solutions of the same electrolyte. Say same electrolyte is used, sodium chloride. Two solutions are there. The strength is say 50 gram per liter and another is 80 gram per liter. The strength of the two solutions like this, in which 1 liter 50 gram of sodium chloride is added, another solution into 1 liter 80 gram of solution, 80 gram of salt is added. So more ions, a larger number of ions are present in this solution. So larger number of ions. Problem is we are not mentioning the concentration. We are just saying 1 ml, but inside that 1 ml, greater is the number of ions, greater will be the conductance. Okay, so you may take 1 ml of this or 1 ml of that. You will definitely find the specific conductance of this solution greater than this solution, since larger number of ions is present in that solution. Even if we are taking 1 ml of both the solution, the same sodium chloride solution gives you two different values of specific conductance. That is the disadvantages. What to do? So that's why we are bringing another conductance term, that is called equivalent conductance. conductance, where we will mention the what? We will mention the concentration. Equivalent conductance, we write lambda Eq. Okay? So, equivalent conductance, before that we will define what is equivalent conductance. Conductance produced due to all the ions present in 1 gram equivalent of the electrolyte is the equivalent conductance. Okay, so once we got the definition, once we understood what actually the equivalent conductance is, then we can have a relationship between the specific conductance and equivalent conductance. So as we discussed, you have to take 1 gram equivalent of the substance. 1 gram equivalent is nothing but the equivalent mass expressed in gram, right? So anyway, let us have a relationship between your specific conductance and your equivalent conductance. Specific conductance and equivalent conductance. Okay, so it's very simple. I have already mentioned you the conductance of 1 ml solution is the specific conductance, and conductance due to 1 gram equivalent of the substance is the equivalent conductance. We will make a plan. We will take 1 ml of solution, and inside that we will put 1 gram equivalent of the substance. Then both of them are at one place. Okay, so if 1 ml of solution contains 1 gram equivalent of substance, so as we know, the conductance of 1 ml of solution is the specific conductance kappa is equal to lambda Eq, because the conductance due to 1 gram equivalent of the substance is equivalent conductance. Once again, if V ml of solution contains that 1 gram equivalent of substance, then we get, you see, if for 1 ml this is kappa, for V ml the specific conductance will be V kappa, isn't it? V kappa, and inside that V ml of solution you have 1 gram equivalent. That means that is equal to the equivalent conductance. Okay, so you see, if the concentration of the solution is, if the concentration of the solution is equal to C gram equivalent per liter, that means if each 1 liter, that means 1000 ml of the solution contains C gram equivalent per liter, then what will be the relationship between the specific conductance and equivalent conductance? You see now. You see, we can write 1 liter is nothing but the 1000 ml. Okay, this is 1000 ml. So this you see, C gram equivalent is present in 1000 ml of solution, where 1 gram implies that 1 gram equivalent of substance will be present in 1000 by C ml of solution. And we had considered that in V ml of the solution, 1 gram equivalent of the substance was present. So if that 1 gram equivalent is in 1000 by C ml of solution, that 1 gram equivalent is present in VML of the solution. So they are nothing but they are the V and 1000 by C are equal. So we can have put this V 1000 by C. So since both 1000 by C and VML of solution contain 1 gram equivalent, so according to this relationship, we will write is equal to kappa into V means kappa into 1000 by C. Kappa into 1000 by C. So this is the formula. This is the formula. Okay. Equivalent conductance is equal to specific conductance into 1000 by C, and C is nothing but gram equivalent per liter, and this concentration term is the normality. So this C is the normality, which is in terms of C gram equivalent per liter. So now let us move to molar conductance. It's a similar term, and similarly we can derive for the relationship between specific conductance and molar conductance. Are you with me now? So you see relationship between. So at first let us discuss what is molar conductance. Okay. So now the molar conductance. You see, in molar conductance, the concentration taken is 1 mole. Like you were taking the 1 gram equivalent of the substance in case of equivalent conductance. Here you are taking the 1 mole of the substance. So the definition is like this. Clear? So you have to take 1 mole of the substance and you should get all the ions produced due to it. Now the conductance due to all the ions produced by 1 mole of the substance is called your molar conductance. And now it's simple to have a relationship between the specific conductance and molar conductance. Okay. So by taking similar assumptions, there you were taking that 1 ml of the solution containing 1 gram equivalent of the substance in case of equivalent conductance. Here you have to consider 1 ml of the substance contain 1 mole of the substance, and accordingly when proceeding you will find the relationship between specific conductance and molar conductance. Okay. You write molar conductance like this, lambda m, right? So the relationship will be like this: lambda m is equal to kappa into 1000 by C, but this C is now molarity. So molarity, the concentration term implies moles per liter. Are you getting that? So this is the relationship between the molar conductance and the specific conductance. Now the next thing is to find the relationship between equivalent conductance and molar conductance. Okay, how to do that? See, we will take an example: H2SO4, sulfuric acid. Its 1 gram equivalent is nothing but equal to gram equivalent mass is equal to 98, its molecular mass, divided by 2, because it's a dibasic acid, it gives 2H plus ions, so 98 by 2 is equal to 49 gram. But its 1 mole is equal to molecular mass So when you are calculating the equivalent conductance, you have to take the gram equivalent mass, and when you are calculating the molar conductance, you have to take the 98 SI, its molar mass. We have taken example for sulfuric acid. It can be calculated for any other compound. So what happens here? You see, but the number of ions present in that 98 gram is almost double the number when it is 49 gram. So which will be that means larger in case of sulfuric acid. So that means the molar conductance is now just 2 times the equivalent conductance. Are you getting it? So definitely the number of ions present in 98 gram is almost 2 times the 49 gram. That's why the molar conductance is 2 times the equivalent conductance. So lambda m is equal to 2 into lambda eq, equivalent conductance. So where does this 2 come from? Okay, so this 2 is coming from this 2. Are you getting it? So since H2SO4 ionizes as 2H plus SO4 2 minus. So total charge of cation. So total charge of cation is equal to 2. This 2 into plus 1, 2 comes here. Okay. So, for example, you are taking example 2, aluminium chloride. Okay, it ionizes as Al3 plus 3Cl minus. So, total charge of cation is 3. Total charge of cation is 3. So, this in this case, lambda eq into 3, lambda eq into 3 will be lambda m. Are you getting it? So that factor, that means, or simply you can tell lambda m by lambda eq is equal to 3. So the relationship between implies that the relationship will be relationship between relationship between lambda eq and lambda m will be lambda m by lambda eq is equal to z is equal to total charge of cation. Sometimes we take it valency, Z as valency. Did you get me? So this is the first part of this video.